Hello everyone, and welcome to the LS Telcom showcase. In this showcase, we like to present you the LS Observer, the LS Telcom solution for automatic monitoring of the spectrum, and also how we can use this in order to evaluate and to measure the interferences in the coexistence of 5G and FSS in the C-band. And for the presentation, I would like to introduce you Abel Philippe, my colleague, which is the product manager for the spectrum monitoring solution and for LS Observer. Philippe?
Okay, thank you, Marian, and welcome from my side. My name is Philipp Abel. I'm the responsible product manager of our spectrum monitoring solution at LS Telcom, and I will present to you today our automated spectrum monitoring solution, LS Observer. Yeah, what is LS Observer? With LS Observer, we, LS Telcom, have created a sensor-based automated spectrum monitoring system. What does this mean? Spectrum monitoring, you can see here a typical spectrum monitoring view. This is a screenshot from our CMS software. So you can see a power versus frequency chart. So you can see all the signals. Here we have the FM signals, and with a linked waterfall chart, so you can see the signals over time. But LS Observer is much more than this traditional monitoring. We have sophisticated feature where the LS Observer automatically can identify anomalies in the spectrum, for example, interference, illegal spectrum usage, like for example, jamming. It will permanently and automated monitor the spectrum, and in case of such an anomaly will automatically trigger an alert. And then if you have such a situation like an anomaly, like an interference, you want to know where is the interference source. And with LS Observer, you can then locate the source based on different technologies like direction finding, time difference of arrival, or our unique technology gain ratio of arrival. LS Observer is sensor-based. Here you can see our hardware portfolio. So we have various monitoring units for different applications. So from fixed monitoring to portable, semi-fixed monitoring, and even we have a fully drone-based system for spectrum monitoring. Later to the details. All those monitoring units can be connected together. Here you can see a typical network for a national regulator. So we have a few mobile station, portable equipment, as well as fixed station. Everything can be connected together and remotely controlled with our CMS software. And also you can control, for example, from a mobile or portable equipment, other networked stations. With LS Observer, you can do for sure all the manual interaction, but what it's standing for is its automation. So we have automated recording permanently of the entire spectrum of interest based on then automatic violation detection, which I already mentioned, with the automatic identification of anomalies, and then the source can be located with various technologies. What does LS Observer consist of? So on one side of the hardware, our remote monitoring unit, so like fixed monitoring unit, portable, or even our drone-based system, and we have our own unique direction finding system. Everything is controlled by one unique software, the LS Observer CMS Central Monitoring Software. And this combination is LS Observer, which allows a wide range of powerful features. Here you can see the inside of our remote monitoring unit, whether if it's a portable one or fixed one, the major components. So besides the receiver, internal processing power, a modem for network communication for remote control. We have a large internal storage, and this reflects the philosophy of LS Observer to permanently store everything. You don't need a permanent remote connection to a headquarter, to a remote server. At first, everything is stored locally, that in case you have a bad bandwidth or even no connection, no data is lost. And later, as a user, you can simply assess the storage of the monitoring unit and can download exactly the portion you need for your analysis. And so you can do everything live, but you can do a lot on stored data, and that's what LS Observer stands for. So you can use stored data for many things like the detection, analysis, and the quantification, and even the localization of interference which occurred in the past. Yeah, with stored data within LS Observer, you can set a reference baseline for future measurements in order to detect anomalies. You can create meaningful long-term spectrum usage statistics and report to support the spectrum management process. For example, in the way of using spectrum occupancy data, where you can see the spectrum utilization over time, where, for example, you can see if a channel is permanently used, if a channel is free to use, or only sometimes blocked. And what is our newest innovation? You can make meaningful spectrum usage and coverage maps with our web-based solution Spectrum Map. I will later show you some details to this. But first to the hardware, to the fixed monitoring units. So this is our unit for permanent outdoor monitoring. It includes everything which LS Observer stands for in a really compact form factor. You can easily install it, like you can see here on this example, on a rooftop, on a lantern pole, or on the left side, it's our demo system here in Germany, just on a small mast. And the good thing is with it, as it's so compact, you can install it directly next to the antenna, so you don't have cable losses. Then our transportable monitoring unit, it has two use cases. One use case you can see on the left side, you can equip a vehicle with it and perform measurement drives. The other use case is for temporary fixed measurements. That means you can place it on several positions, for example, like we did here for a large European airport for spectrum inventory. We put it on one place, let it run for 1 week. It captures everything, all the activities in the spectrum, and then it was taken to another place. We did the same, and then as a result, we analyzed all activities in the spectrum, all frequency usage. Was it already known by the airport operator, or are there illegal usage or existing interference? That would be one use case. It's called spectrum inventory. Then our protected portable unit, it's the unit for rough infield conditions, also used by our military customers. It includes in battery, you can directly make infield measurements with it, and it includes a control screen with a CMS software, but you can also close the box and use it as a remote monitoring unit. Then for emitter hunting on the last meters, we have our portable monitoring unit. You can see on the left side the use case of signal homing. So you have a handheld directional antenna and our software which supports the use case with a power bar chart and acoustic feedback. So you can search for emitters on the last meters, for example, also indoors. Then we have our airborne monitoring unit. This unit is fully integrated system, so everything which LS Observer stands for inside a drone, airborne monitoring unit. I just see a black screen. Can you still see my slides? Just a second. Can you see my slides? Can anyone give me feedback?
Yes.
Good, thank you. Perfect. Sorry for this. There was just a screen blackout. Okay, so our airborne monitoring unit is for several use cases. So it's interesting if you measure on the ground with ground-based monitoring equipment. And if you fly up with a drone, you can see suddenly signals appearing in the spectrum, yeah, because you overfly any obstacles, so you increase the coverage radius. And you can see on this drone, there's also a directional antenna installed, so you can do direction finding with this a drone-based solution. In this case, where you in urban environments where you don't have a line of sight to a searched emitter, if you use ground-based equipment, you can fly up and get line of sight and get really clear and good direction finding results. Another use case you can see here on the right side on this animation is for microwave link measurements. That means microwave link, you need to go inside the Fresnel zone. Oh, there's again something with this screen. Let me look. Now it's back. Sorry about this. You need to fly.
You are not back yet.
Now back, Marian?
No.
Let me check quickly. Sorry about this. Back now?
Not yet.
Then
Now it's okay.
You saw it?
Yes.
Now?
Now it's okay.
Okay, good. So sorry everyone for this small technical problem. So the fixed link measurement, it means you need to fly inside the Fresnel zone of the link to see something, yeah. And this can be perfectly done with our airborne monitoring unit to measure microwave links. Then we have our own direction finding solution, our AOA1XX system, that can not only perform direction finding live as usual on the market, but also based on a stored spectrum. And this is a real interesting use case. It's called DF time travel. So you can pick up from a stored spectrum every signal and perform direction finding on it. It's available as a version for fixed monitoring and for mobile based monitoring. Then to our LS Observer CMS software, is a modern design, user-friendly monitoring software. You can centrally manage a complete network of LS Observer monitoring units. It includes a wide range of features like normal scan and fixed frequency mode, automatic violation detection, ITU compliant signal parameter measurements, direction finding, this just mentioned DF time travel for direction finding based on stored data, our technologies to locate an emission based on omni antenna, GRA plus and TDOA, recording, spectrum occupancy measurements, channel analysis, reporting, drive test mapping, and many more. A few features I want to show you today. I've prepared a few videos. Here you can see now the CMS software monitoring system overview, where you can see all connected monitoring units and their position on the map. To start a measurement, just go to measurement control, and now you can select any unit. For frequency range scan, for example, type in a start and stop frequency of the scan, add the receiver parameters. And now you can see the spectrum in a power versus frequency with a linked waterfall chart to see the signal over time. You can at any time just zoom in, move the chart. It's pretty interactive, the whole thing here, to analyze signal in detail. You always have the mouse over of the current mouse position. You can always go back and you can apply different curves like maximum hold, average, and minimum curve. Then you can add markers put on a specific signal to see the information for the signal, like the sender frequency and the actual level. We also have markers which automatically apply to the peak level. That's a basic operation of CMS. Then to the automatic violation detection. Remember, this feature can permanently 24/7 run, and this feature checks if the measured spectrum is conformed to the user-defined reference masking. So you can create as a user masks for each channel of interest, and if those thresholds defined in this mask are exceeded, you will get an alert. Like for example, in this case here, this is now for ATC. I've prepared now this scenario that at if a signal pops up, you will get immediately an alert. Yeah, that's one option here. You can see just for illustration that you can see how alarming happens. So as soon as a signal pops up, you will get an alert. All alerts are logged in a so-called AVD log file, so you can see the alarm history over time. If you come back to your office, for example, at in the morning, and you can see the alarm history over time. You don't need someone who permanently sits on the screen to look at if there are alarms. Yeah, that's not the sense of AVD. You can connect the CMS to an email server so that you get, as soon as some alarm happens, that you will get an information via emails and you can react. How you can create those masks per channel where you can define the thresholds. You can do this manually for sure, but also, which is more attractive with LS Observer, you have the option to do a calculation. And one option is to import your license stations from Spectrum Management. So if you have a database with all the license stations, LS Observer CMS calculates the expected receive level of the individual license station at the location of the monitoring unit. So like you can see here, the picture on the right side, if you have the information of the radiated power of the station, it can do a wave propagation calculation internally, also considering terrain and clutter data, and will give you then the level which the monitoring unit should receive the license station if it transmit with the radiated power according to the license condition. So with this, you can really monitor if the license conditions are fulfilled. Yeah, if you can use this level then as a reference, add a tolerance around it where the signal can fluctuate in, and so if you have if those tolerance are exceeded, you either have a station with a too high level, or you have a problem like interference, or in the other way, you have an outage. Option 3 is another way. You can do a recording and then take this recording as a reference for AVD. Illustrated in this situation, for example, for the GPS L1 band. In the reference situation, there was only noise, everything normal. So you do AVD takes this as a reference, and if you measure again the next week, then like in the scenario on the right side, if a jammer is active, a GPS jammer is actually a big problem. The AVD will trigger an alert and immediately, and you will get to know this. So AVD identifies that there's an anomaly compared to the recording situation. Then analysis on stored data. So with LS Observer, you can just assess the stored data of a monitoring unit, and you can limit this stored data to the portion you want to analyze. So if you want to analyze only a certain frequency range, you can add this, and then in the recording you can slide through the time and zoom in and to see a signal in detail. For also the option which you can see here is to show spectrum occupancy data. This data is the spectrum utilization over time. If it's red here, you can see the channel is permanently in use. Yeah, going more to the bluer colors, to the colder colors, the spectrum, the channel is only sometimes in use. Like you can see here from the FM, you have a lot of red channels, so 100% usage of the channel. Then you have white, there's nothing, and then you have some blue. And this is the ATC, typical ATC traffic, where only sometimes pilot speaks, only sometimes ground control speak. In between, you have a red line. It's a broadcast emitter. It's called ATIS of the airport, which permanently broadcasts with an electronic voice informations for the pilot, so that this channel is permanently in use. And with the occupancy data, you can really see good the development of the spectrum over time. Here you can see in this chart on the right side in the ATC spectrum that if you read it from the lower end of the screen, that with the timeline to the night hours, that you can see suddenly more white. Yeah, so you can see that the ATC communication traffic is reduced during night, and then in the morning hours again, the traffic is higher. This you can also see from occupancy data. You can see if channels are free to use, how they are used, if they are heavily used, if you have overloads, or if you have free capacity. Then direction finding in geolocation. So with LS Observer, again, we have three options. If you use our direction finding system, you can do direction finding based on AOA, and you can do this based on stored data, not only based on live data, based on a stored spectrum. This I want to illustrate you in this video. So here you can see a measurement from 10 megahertz up to 1 gigahertz, a recording. And now inside this, you can select any signal and perform direction finding for this. That means draw a line of bearing. You just zoom in, click resample, select the signal you're interested in. Just you need to double click, analyze, and then you can plot the line of bearing on the map, and you can see we have another line of bearing plotted here, and you can see perfectly the cross intersection, the triangulation of the bearings. You can also add a heat map to show you the color coding, and so this is how you can triangulate a signal. If you use omni antennas, we have the technology of gain ratio of arrival. This is a unique technology. It takes the power differences received at 3 or more locations. So if a signal is nearer of a monitoring receiver, it for sure receives it with a higher power. Normally in open field, yeah, that's what the typically gain ratio of arrival stands for, also defined by the ITU. But now what we add to this technology is wave propagation calculation. If you have an urban environment, yeah, if you have any obstacles between your search emission and your receiver, the normal gain ratio of arrival technology would work not good. Yeah, and we consider this with the GRA plus because this is why we add this plus, and by this we make GRA to really precise methods. So we include again wave propagation calculation. We consider any obstacles between the searched emitter and the monitoring unit. And here you can see the time difference of arrival. This technology uses the time difference of a arriving wave received at 3 or more locations. Again, we just need to double click on the signal of interest, and then the calculation is done. And again, we have a heat map which is displayed in the CMS software. So you can see the result here, even if it's not the perfect situation for T2A, because the best is that the signal is inside the polygon the sensors are opening. You have a good result here. You can fine tune the color coding a bit, and you can see that red means there's the highest possibility that the searched emitter is inside this. Why we have three technologies? Because, for example, TDOA have a few limitations. For example, the bandwidth of the search signal. TDOA does not work really good for narrowband signals because of the time uncertainty that's limited by physics. That's why for narrowband signals, you can choose, if you only have omni antennas, you can choose then our flexible, our other technologies gain ratio of arrival. So with LS Observer, you're really flexible in doing localization with those three possible technologies. Now, what I wanted to tell you, to show you also today, is our newest and modern innovation spectrum map to visualize big data from monitoring. What it is, you may know this screen you can see here on the top with those dots on a line. It's a typical drive test view. You can also do it in CMS. So you drive along a route and you can see the captured level color coding. So you can see where a level was higher, where it was lower. If you then look on the right screen, we put this to a maximum level. So we make drive test in a whole Shanghai. Yeah, this is Shanghai with a lot of different drive vehicles, also including fixed stations. Yeah. So you can see we have a lot of dots here. And now our spectrum map comes into play. Spectrum map takes all the big data from monitoring of a certain area, like a city, and combine it, fuse it, and present it as a continuous map, like you can see on the lower end of the screen. So it interpolates all the measurement points to show a clear entire map of your spectrum. This is no simulation. This is based on monitoring data of your spectrum in an urban environment, like for example, Shanghai. This is really, really great tool for spectrum management because you can see the real situation of your spectrum. You can visualize, for example, a field strength map for a certain frequency band. So you can see how the frequency is used and where it is used, and you can see the coverage. And all of this is based on a web-based system. You can just assess this via browser. The backend runs on a server or can also run in the cloud. And all you need to do is then just log in, and then you need to define the area of interest where you want to do the calculation of the map. So I define a vector here, and then you have different application. Now the band situation is the most used application. It will give you a field strength map. So you can see the field strength distribution in dB microvolt per meters, color coded here. You can see the scaling here. You can always adapt this as a user manually. Here you can see the GSMR, the railway frequency, where you can see that around the railway the power is higher. So you have an entire and continuous field strength map. What you can also add is a various map here with coverage. You can say from a certain limit it's covered or not covered. Then you have also the option to dynamically slide through the spectrum, for example, through a certain band, and it will go step by step through the channels and will show you how the spectrum situation changes. And this you can do not only channel by channel, so over frequency, but also over time. So you can see, for example, each day of the week, you can see a map and you can see how the spectrum changes. Yeah. Another example we did here was just this year in Dubai. This was a really good use case for spectrum map. We produced such a nice spectrum map, which you can see here. What you need for this, in this case, we did this only on just one vehicle. We put a standard vehicle, just a small antenna, magnetic antenna on top, and put a PPU inside our LS Observer unit inside the vehicle and drive around the entire city area. We produced 268 gigabytes of data from 6 hour 30 drive tests, and then everything was automatically uploaded to the Spectrum Map server, and the Spectrum Map backend processes this, and the user can then get browser view on the web-based application. What can you do with Spectrum Map? What are the use cases? So at first, like you can see here, you can see the coverage for a certain band. You can evaluate, for example, which mobile provider provides the best coverage in your city, for example, for 5G. And what is the general coverage of 5G if you take all the bands of all providers that you can see. So one thing is coverage, but if you also look on the other side, you can also map the uplink. Yeah, you can see the frequency usage, where, for example, narrowband IoT is used. Yeah. You have a coverage of narrowband IoT, but where it is really used, or where you have high Tetra or PMR usage, where you have high or low dense usage, so you can identify overloads, you can see what is happening. You can also just see from this map if you have illegal emitters, yeah, because you have so much data, you have a continuous map. If you have a hotspot somewhere where it does not belong, you see, okay, this must be an illegal emitter, because you can also display the emitters with Spectrum Map from your spectrum management database. This is a really a good decision basis for frequency assignment and reallocation. So you can see based on real data, not based on calculated data, you can see what is the spectrum situation, and can then evaluate if a certain frequency can be assigned, or if a certain frequency is not used or has not a good coverage. You can think about reallocation. Also, modern technologies like spectrum sharing concepts are possible with this. So you can see, okay, a certain frequency is only used at a certain area, so you could assign for other area this to another user. That's also possible. And another application would be to evaluate radiation hazards. You can make a map of radiation hazards for the whole city, to prove the public that all limitations are not exceeded, yeah, that everything is inside the limits. That would be also an application for Spectrum Map. How we see in future the data collection, how we see to develop this, is that the data gathering in future, because Spectrum Map lives from big data, that you can use public transport for this. And here we do already some developments, that you just simply put your monitoring unit and the monitoring system, for example, on a bus. A bus drives permanently through the entire city, can collect a lot of data, or to taxis or garbage trucks, can collect a lot of data day by day, and you can make really use out of this big data with Spectrum Map. You have a really high data density by using public transport, instead of having, for example, two or more vehicles with somebody who drives each second day. You cannot achieve this density like with public transport. So we see this as a real future of urban monitoring. You see also cells are getting smaller and smaller. You need a really high density of data, and with this application, we see really the future of spectrum monitoring. Okay, now this is the end of my general presentation. Now Marian will talk something especially to the use case of 5G to fixed satellite service interference measurement. So Marian, please continue.
Thank you, Philip. Very good presentation. So, what you saw is the how the LS Observer concept can manage very easily all the needs of a regulator. Another advantage of LS Observer concept is very flexible and can also be used for some specific task. One specific task, which is very hot topic nowadays, is the 5G to FSS interference measurements in the C-band. What you need to take into consideration is the fact that the interference levels should be something like at least 10 dBs under the thermal noise. For example, if we consider the regulation issued by FCC, their threshold level of interferences is 14 dBs under the thermal noise. A second fact is the interference is noise-like. So you'll not see anything on your screen. It will be just a noise, which is 14 dBs under the thermal noise. So this is a schematic of a general concept how you should measure this kind of interferences. And of course, you need also an INT scanner to try to decode the information. So once you see the interference is higher than the threshold, you need to have a possibility to identify the base station, which is creating that interference, because maybe in the beginning you'll have only a couple 5G stations, but will reach the maturity, you'll have probably hundreds of base stations in the vicinity of an Earth station. So where the LS observer concept will have huge advantage is just replace the RTSA, meaning a real-time spectrum analyzer, with an LS observer unit. So now you'll be able to automatically measure the level of interferences, to have statistics on the level, to define automatic violation detection. Why is this? Because you see 1 or 2 dBs interference higher than the threshold can create real problems to the station, and most likely an human operator will not be able to see this increase of the noise, because noise itself is a statistical representation of an energy, meaning the noise is not flat. It will vary because this is natural way of how the noise is. And another advantage is the reaction speed, because with LS Observer, you have the possibility to proactively measure the spectrum. So once an Earth station will report an interference, you don't need to start a monitoring session. You can just go back in the time and perform an search, meaning a search after a violation detection. You can perform automatic violation detection searches on store results, and in that way you'll be able to identify an interference which happened even before it was reported. Why is this very important? Is because the 5G interferences will be mainly created by the out-of-band transmissions, and the out-of-band beamforming is not correlated with the in-band 5G beamforming. This means there will not be a clear rule when the interference will occur, and it might happen only when the load of the base station is higher than a threshold, or when the base station is transmitting in a specific direction, which is not mandatory to be the Earth station direction. So this is why LS Observer can really deal with this kind of very difficult measurement and very difficult monitoring, meaning the 5G measurements, 5G interferences, which, as I said, are noise-like and much lower than the thermal noise. So if you have any question, maybe you can raise it right now, or of course you can send them to us even after the conference.
Yeah, so just with this question slide, so let us know if you have any question to my part or Marian's part now. So we have 5 minutes left, so we will just wait a second if some questions come in. So I see no questions so far. Maybe I can jump over my presentation slides again, that you remember everything which was presented. Marian, can you see the screen I share
Mm,
with
not yet.
presentations? Okay.
It's your very beautiful picture now. Okay, now
Okay.
it is there.
So I will just quickly slide through those slides. Yeah. So if you see any question here, just to remember the slides, just please raise it. We're happy to answer your questions.
Just like a final mention, just remember that with LS Observer, all the spectrum analysis can be performed also on saved results. And these also cover the AOA geolocation. Okay, then.
Exactly. Yeah. Okay. No.
I think.
No. Any
Yeah.
questions? Just now see it. Okay. Okay.
Okay.
Just get information of a question. Can you describe again quickly the AMU solution, please? Okay, yeah, thank you for this question. I will just describe it to you again. Just let me open the slides for this. So yeah, the use case for this, here we have a receiver, a processor, a storage, everything integrated on a special drone, especially for this integration. Yeah, it's just not like you put a receiver below a DJI drone. Yeah, that's a fully integrated system. Yeah, it's also shielded. Yeah, you need to have a look on the rotators. They produce noise, so it's a fully integrated system. You can see here it without cover to show you the inside. You can rotate the antenna, and the use case is one use case is to do standard monitoring, yeah, to if you fly up in an, for example, an urban environment, you increase the coverage area. Yeah, you can overfly any obstacles. You can get signals in which you don't see on the ground, and then you can do direction finding by turning the drone 360 degree. You get a polar chart, and the software can calculate a line of bearing for this, and by this I can just give you this use case. Yeah, do a direction finding with a handheld antenna, where between you and your searched emitter is a building. Yeah, you can forget it. Yeah, you don't get good results or even no results. So then if you fly up and overfly this building with this AMU, you get line of sight to the searched emitter, and then you can do a really good direction finding. That's one application. Another application is to measure fixed links. You can directly fly inside the microwave link. You cannot measure anything or only low on the ground. So to measure if a link is active, or to measure if the A or B side has problems, you can do this with the Airborne monitoring unit. Also, we do another field. We have this drone application, our subsidiary called Colibrex. They use it also to measure broadcast antennas. They fly around an antenna and can then produce the antenna diagram to check if the antenna radiated according to the theory. And also it used in another application to verify the instrument landing system of an airport. This was before done via airplane. Now it can be done also with the Colibrex drone. So really interesting use case. If you want more information, just visit the Colibrex or LS Telcom website. Okay, any more questions, Marian? I don't see them because I share my slide.
No, anyway, I restate our invitation. So if you have questions, just send it to us at any moment, even after the end of the conference.
Okay, good. Then I think we're through.
And thank you very much for your patience.
So yeah, thank you very much.